So the first part was we had to figure out. Let me just give a brief. We can start with a part one again. The first part was we had to explain the relative acidities of ethanol and phenol. Remember, alcohols were very less acidic. Okay, they only reacted. They would only react with sodium and nothing else. They don't tend to lose H plus one ions. So they would only react with very reactive metals like sodium. And the reason for that was that the OH group in an alcohol would dissociate, but very, very weakly. The dissociation was even lesser compared to water. And why was it lesser? Because it had a carbon chain and alkyl chain which had an electron donating effect. So remember, carbon chains always have electron donating effects. Uh, as a result, the negative charge over here, when the H plus one leaves, the negative charge over here has a very high charge density because the carbon chain is pushing its electrons towards the oxygen. So because the electrons over here and the negative charge density over here is very strong, it's going to attract the H plus one. So it's going to attract the H plus one back again, and the dissociation will not happen. Whereas, why does dissociation happen more in phenols? Phenol were kind of more acidic. They would react with sodium, a reactive metal, but they would also react with bases as well. But they would not react with weak bases like carbonates. So no reaction happened with carbonates for phenols. So phenols were more acidic compared to alcohols, but not that acidic. They were weaker acids compared to carboxylic acids. So the reason the OH in a phenol would dissociate more was that the oxygen, the negative charge, the electrons that have accumulated on the oxygen once the H plus one breaks off, it would overlap with benzene's pi electron cloud, which would decrease the charge density over here, and because of that, the H plus one would no longer be attracted to this. So there was more chances of dissociation happening. Now, is this clear, Anam, Sara? Is this clear?
Yes, sir.
Now, the next part of the question is about electrophilic substitution, and I'm just going to give you a. Uh, they're asking for the formation of the organic product D. They did two electrophilic substitution reactions for benzene, mainly that you have to study. One is the bromination or chlorination of benzene, and the other one is nitration of benzene, which happens with nitric acid. And the reaction is that a normal benzene needs a catalyst. So if you have a normal benzene, let me draw a normal benzene. 1 second, let me add some people. So if you have a normal benzene with its electron cloud, uh, remember the electron density of benzene is not very high. Okay, the carbon is sp2 hybridized. What that means is that four of the electrons of carbon are bonded and they are fan shaped. The electrons are pulled in different directions. There is, the middle ones are all carbons, and the fourth electron in benzene, which is a p orbital, is not involved in bonding initially, and they would all tend to overlap, and they would tend to overlap and form pi electron clouds. So, so the fourth electron becomes delocalized, and but the electron density is not very high. Reason is that the electron over here is not only overlapping on, it's overlapping on both sides. Its electron is getting distributed and overlapping with the carbon on the left side. It's also overlapping and being distributed towards the carbon on the right. which is why the electron cloud is more distributed. So what happens is normal benzenes, they're not able to polarize the bromine molecule because the electron density is not very high. It's more distributed. So if bromine comes and bromine gets polarized, the electrons get repelled by the electron cloud over here. Uh, this bromine gets a partial negative charge. This bromine gets a partial positive charge, and it's going to try and attract one of the p orbitals towards itself. But since the polarization is not very high, the positive charge over here is not very high enough, it's not going to be able to attract this electron. Okay, remember the electron density is very distributed, so the repulsion and the polarization of the bromine is not very, very high. So, which is why normally you need a catalyst, which is usually FeBr3 or AlBr3. And Fe, as a transition metals, they have this tendency to attract electrons. So the FeBr3 catalyst is going to pull the electron from the other side, and that would polarize the bromine molecule further, and that would help in breaking this bond heterolytically. And this Br becomes positive, and then it gets attracted to the electron over here. And that's how a normal benzene would react. A normal benzene needs a catalyst. But when it comes to phenol, what happens in phenols? When it comes to phenols, you don't really need a catalyst. And the reason is that there is an OH group. So what does the OH group do? So instead of H on one side, there is an OH group. Now the OH group, oxen has these extra lone pairs. And these extra lone pairs, they tend to overlap with benzene's pi electron cloud, and the electron density on the 2, 4, 6 positions, it increases because the lone pairs of oxen are overlapping with that. And the electron density also increases right on the opposite side because of the lone pair, because all the other electrons, they get repelled by the electrons over here and they get accumulated on this side. So because of that, and let me focus on this. So because of the lone pair overlapping with benzene's electron cloud, the electron density on these carbon atom increases, and all the other electrons in the benzene electron cloud, they get repelled to the other side, which makes the electron density on the other side higher as well. So now when the bromine molecule approaches this, you don't need a catalyst. The reason you don't need a catalyst is because the electron density is significantly higher. And the polarization in this case is going to be much greater. So there's going to be, if the bromine molecule approaches, the electrons in bromine are going to be repelled by the higher electron density because these extra lone pairs are also overlapping with the electron cloud, which increases the electron density over here. And the bromine molecule would then need no help. The heterolytic fission would happen on its own. There is no need for a catalyst on the other side that should be pulling the bromine. All the repulsion can happen from this side. The electrons can be repelled by the electrons over here, and a reaction can then happen. ठीक है सारा, is this clear, Abu Rera?
Yes, sir.
Yes, sir.
So this was called an activated benzene. It was a 2,4 directing group. OH was a 2,4 directing group. Anything that has lone pairs, there were three 2,4 directing groups. One was OH, the other one was alkyl chains. Carbon chains pretty much do the same thing, and the third one was NH2. They're all they're all 2,4 directing groups, and what they do is that they activate the benzene. They make the reactions a lot faster. So the conditions required for bromination and even for nitration are very, very mild. For bromine, the only condition that's needed is aqueous bromine. Okay, that's pretty much the only condition that you need. You don't need any catalyst. And what's going to happen is if you use dilute nitric acid, so if you use dilute nitric acid, an NO2 group might get attached on the second position, or there might be another chance, which is that the NO2 group might get attached on the fourth position. And if you use aqueous bromine, so because the benzene is so much activated that bromines they get attached on all positions, the 2, 4, and 6 positions. So remember, the OH group is an activating group, and it increases the activation of benzene. The reactions become a lot faster, and not only do they become a lot faster, more bromines get added on the OH on the phenol uh, on all three positions. With dilute nitric acid at a very low temperature, only one NO2 gets attached. Even with NO2, the NO2 usually gets attached on all three positions because the benzene has a very high electron density and it's able to attract the NO2 plus 1 electrophile very, very strongly. Uh, the reason we are only adding one NO2 is because the conditions are very, very mild. If he had used concentrated nitric acid at a higher temperature, then all three positions NO2 is going to get attached. Okay. So name the mechanism of this reaction. The mechanism of this reaction is electrophilic substitution. And then they're saying phenylamine reacts with aqueous bromine to give compound F. Describe the appearance of compound F. Remember, this is again it's a white precipitate that you get uh, when bromine reacts with phenol or phenylamine. And then they're saying phenylamine reacts with nitrous acid to form a diazonium salt. State the conditions for the reaction. So for this, I think we should open our notes to go over instead of me writing the whole mechanism. Just 1 second. Okay, now the azodized part. Just 1 second. Let me quickly. I mean, this is all about comparison of acids. Okay, this part. So we'll just quickly revise this. Okay, what's azodized? Acid dyes are very stable dyes. They're used in paints very often. The starting material of an azode dye is phenylamine, which is NH2. It's benzene with NH2. And the first part is that you react NNO2 plus and HCl are mixed together with, and the temperature is less than 10 degrees centigrade. This is something that you have to remember because azode dyes come very frequently. Uh, the first part is under these conditions, a diazonium ion is formed, which is very, very unstable. It's N triple bond N plus one. The temperature is therefore kept below 10 degrees centigrade. It's a very unstable diazonium ion. And it decomposes very quickly because if you increase the temperature to greater than 10 degrees centigrade, hydrolysis happens. If water is present, the whole thing would break down to form a phenol and an NH4 plus 1. The N triple bond would simply break because it's very unstable. Uh, then this thing is an electrophile. What you do is that you take this diazonium ion, which is a very unstable ion, and you react it with an activated benzene. An activated benzene is the one where the benzene either has an OH group or an NH2 group attached. The lone pairs are going to mix with the benzene, and the charge density would be higher on the benzene. So the N triple bond N plus one would be very strongly attracted to this benzene. It's and not only is it going to get attracted to it, it's going to borrow electrons from it, and it's going to bond with this carbon atom, which it does, and an azo group is formed. So the N triple bond N plus one goes and bonds with the benzene, the activated benzene. It has to be an activated benzene. The conditions for this reaction are NaOH, aqueous, and this azo dye is formed. So remember this step. This thing comes very frequently in your exams. Almost every paper has a question on azo dyes. So remember the whole process. So this question that we were doing, that was on azo dyes. He's saying phenylamine reacts with nitrous acid to form a diazonium salt. State the conditions for this reaction. The main condition for this reaction was that the temperature has to be kept below 10 degrees centigrade. Basically, he's talking about this part. Nitrous acid, this is HNO2. Uh, HNO2 is actually formed when NO2 and HCl are reacted together to form HNO2. And the temperature is kept below 10 degrees centigrade. That's how you're going to get a diazonium ion. So that's the first part. And then he's saying in the next part, the diazonium salt reacts with an alkaline solution of phenol to produce a colored compound G. So draw the structure of G. So I don't think they're specifically talking about any. He's talking about phenylamine. So he's specifically talking about drawing this structure that the diazonium salt reacts with an alkaline solution of phenol. So he's basically talking about this part, which we just did, that the diazonium ion reacts under alkaline conditions. It reacts with a phenol uh, on the 2, 4, or 6 position, which is this one. The electrons get attracted and you get this. So he's basically asking you to form this. The diazonium ion reacting with phenol. So this is what you have to draw. Okay. Sarah, is this clear? Aisha, is this clear?
Yes.
And the next part is so that's all about azo. Remember, azo are very, very important. They're always appearing in the exam. Now, compound H, part C is compound H is a primary amine which has 3 peaks in its carbon 13 NMR. Now we're talking about carbon 13 NMR. So what is carbon 13 NMR? Next page, just 1 second. Which part is this? This is C. Take this one. So carbon 13 NMR. Carbon 13 NMR is that the carbon 13 is an isotope of carbon 12 and it has a magnetic field. For example, this carbon atom over here has a magnetic field. If you put this molecule in an external magnetic field, like inside a powerful magnet, this is called an aligned spin or an aligned magnetic dipole. Just like a compass needle pointing, it points north. If you put this molecule in a powerful external magnetic field, all the carbons and the magnetic fields are going to point in this direction. The magnetic field because of the nucleuses would point in the same direction. But then you can make them point in the opposite direction if you make them energetic by giving them radio waves. These carbon nucleuses or nucleons can absorb energy from the radio spectrum. And when they absorb energy from the radio spectrum, they become energetic and they go into opposing spin or opposing magnetic dipole. That requires energy because by default, this tiny magnet, the carbon nucleus is behaving as a tiny magnet with its magnetic field. By default, it's going to point in the direction of the external magnetic field, just like a compass needle pointing north. To make it point in the opposite direction, you need to give it energy. You need to forcefully point it in the opposite direction. So that's exactly what we're trying to do. We are making carbon energetic so that it's going to absorb a specific frequency. And let's call that frequency F1. And this frequency depends on the chemical environment. It depends on the shielding of the electrons. It depends on what it is bonded to. Because every time it's going to experience a different amount of magnetic field because of the shielding, the electrons and the atoms surrounding it. So if the chemical environment is different, a different frequency is going to be absorbed for resonance. This is called resonance, going into the opposing spin. So we need to figure out how many different carbon environments are there in this molecule. And when I talk about carbon environments, it has to be uh, the carbon environments. They have to be different. I mean, for example, they should be bonded differently. For example, if you look at the carbons over here, the ones at the end, these two, are these carbons in different environments or the same environment?
Sir. Same.
ठीक है, they're exactly same. ठीक है, बुरा same है कि नहीं है?
Same.
ठीक है, they're exactly same. Which means they're shielding, the nucleus would be shielded in exactly the same way, which means that they're going to experience exactly the same magnetic field, the external magnetic field, and which means that the same amount of frequency would be needed to make them go into opposing spin. So they would resonate at one frequency. Achha, then similarly, these two hydrogens, carbon, sorry, they are in exactly the same environment. The two carbons with the CH2 group, I mean, these CH2 groups. Focus on the carbons, they're bonded in exactly the same way. So they're going to resonate at one frequency, let's call that F2, and this carbon has a different environment compared to all the others. So it's going to resonate at frequency F3. So they're going to be three resonant frequencies. And actually, they weren't even asking for that. They had already told us. I thought they were asking for that. They'd already told us that there were three peaks. But anyways, then he's saying that an isomer of H, this one is another primary amine. So it has to be a primary amine which also has three peaks in its carbon 13 NMR spectrum. Use this information to suggest the structure of J. So it has to be an isomer and it should also have three peaks. So it should also have three peaks. And what's a primary amine? So the first thing is, what's a primary amine? Primary amine is when the N is bonded to just one carbon chain. Okay, that's a primary amine. I mean, this one over here is a primary amine because the N is only on one side is it bonded to carbon chains. Uh, so this is a primary amine. So we need to come up with another primary amine, and it should have three environments. So let's think of a molecule. Let me draw random isomers. For example, five carbon atoms. That's so we have five carbon atoms, right? So let's say this is NH2. This is CH2. But let's put the H's together. So this is CH2, this is CH2, and this is CH, and this is CH3. So can anyone tell me how many carbon environments are there in this molecule?
Three.
I mean, look at the two CH3s. Are these the same environment or different?
Same.
ठीक है,
Same.
ये दोनों same है, ठीक है, exactly same है. So then you have this CH, that's different. This one is different from all the others. This one is also different from all the others. So these two are exactly the same. That's frequency F1. This is frequency F2. These two CH2s are definitely different because this CH2 is bonded to something else. This CH2 is bonded to NH2. So the shielding and the groups are different. Anyways, we're not getting four frequencies. We're not getting four peaks. क्योंकि उसने कहा था it was supposed you're supposed to get three peaks. So think of another isomer. What could be another isomer? Uh, I mean, let's try. So that's one. That's the second one. How do we make it three peaks? We have five carbon atoms, right? One second. That's six carbon atoms. Let's say there's another C, uh,
लगा दें नीचे.
and then there is NH2. I think this would do the job. Uh, ठीक है, add in the hydrogens. This is CH2 and this is NH2. ठीक है, this exactly has three environments. Because if you look carefully, ये जो end वाले CH3 है ना, they're all exactly the same. We clear? I mean, the CH3s at the end, they're exactly the same. So they're going to resonate at frequency, let's say F1. This carbon is different. It has a different bonding in different environment, and this carbon is different. So that would be the frequency of 3. Is this clear?
Yes, sir.
Yes, sir.
ठीक है, तो ठीक है, इस पे सोचना पड़ा था. Then he's saying कि another isomer of H is the tertiary amine. I said, remember tertiary amine. Tertiary amine is when the N is on all sides bonded to a carbon chain. That's a tertiary amine. And he's saying it has three peaks in its proton NMR spectrum. One of the peaks is a doublet. I said, now the whole thing has changed. Uh, and say circle the proton responsible for the doublet. Now this is about H NMR. ठीक है, the proton NMR. अच्छा, what's the difference between carbon NMR and H NMR? H NMR का भी वही कहानी है कि उसके अंदर ना you don't focus on the carbon, you're basically trying to resonate the hydrogen. Hydrogen also has a magnetic dipole, जो external के साथ align हो जाता है. You give it energy, it absorbs a particular frequency, and it goes into the opposing spin, uh, because it becomes energetic. So and the resonant frequency depends on the environment, depends on the bonding. Now he's saying, so firstly, let's analyze the whole molecule. ठीक है, even though it's not required, let's analyze the whole molecule. The first thing is how many different hydrogen environments are there? Uh, these two hydrogens. Now focus on the hydrogens, which is pretty much the same as we were focusing on carbon. It's basically the same thing. So these hydrogens over here and these hydrogens over here are bonded in exactly the same way. So that means that's one environment, and these hydrogens are going to resonate at frequency F1. This hydrogen over here, it has a different environment than the rest, so it's going to resonate at frequency F2. And these hydrogens over here, they're in the same environment because they're both bonded to nitrogen. So that means they're going to resonate at frequency F3. So there's just three peaks. Usne wahi kaha, it has three peaks. But one thing happens in HNMR, and that is that the neighboring hydrogens, they cause interference. अच्छा, उसका एक rule होता है, which is known as the N+1 rule. What is the N+1 rule? N+1 rule is that the hydrogens immediately on the neighboring carbon atom, uh, बिल्कुल साथ वाले पे, they would cause interference. So if there is one neighborhood H, साथ वाले carbon atom के ऊपर ना, there's one H neighbor. So because of interference, the peak would be a doublet. Doublet means it would split into two, because there's going to be some interference because of the neighboring hydrogen. If the neighborhood has two hydrogen protons, the peak would be a triplet. मतलब उसकी पीछे लॉजिक ये थी कि लेट्स से यू हैव अ हाइड्रोजन ओवर हियर, वो रेजोनेट करने की कोशिश कर रहा है, ठीक है, इट्स अलाइंड with the external magnetic field, and then it absorbs the frequency, and then it gets but let's say this is the powerful external magnetic field, तो वो उसके साथ अलाइन हुआ हुआ है, ठीक है, जैसे कंपास की नीडल अलाइन हो जाती है, तो इट्स अलाइन विद द एक्सटर्नल मैग्नेटिक फील्ड, राइट? अब इसके नेबरहुड में ना लेट्स से देयर आर टू हाइड्रोजन्स, देयर इज वन ओवर हियर एंड वन ओवर हियर, बिल्कुल साथ वाले पे, वो क्या करेंगे, वो अपनी मैग्नेटिक फील्ड भी ना बीच में ऐड कर देंगे. So what's going to happen is that this H proton would actually in total experience a bigger magnetic field. Okay, it's already experiencing an external magnetic field, but the neighboring H protons, their magnetic field is also going to get added, and it experiences a much bigger magnetic field, which is why it's much harder for it to resonate, much harder for it to go into opposing spin. It has to absorb a lot of energy now. Okay, so it's experiencing a slightly bigger magnetic field. Then it could be that the neighboring hydrogen protons could be misaligned, could be in the opposing spin. So if they are in the opposing spin, so that means they're going to cancel out the external magnetic field. So ये जो H proton होगा ना, that would experience a slightly lesser magnetic field because their magnetic fields and the external magnetic field, they're going to try and cancel each other out. So this H proton would experience a slightly lesser magnetic field, just very tiny, क्योंकि इसकी magnetic field इतनी ज़्यादा नहीं है. It's a very small magnetic field. So this H proton would experience a slightly lesser magnetic field, and it would be slightly easier for it to resonate because वो जो neighboring H protons हैं, they're cancelling out the external magnetic field. तो वो different frequency हो जाएगी. So the frequency would keep on shifting for this H proton because of the interference of these neighborhood H protons. ठीक है, ये clear है?
Yes.
So the rule was that if the neighborhood has one H, then the peak would be a doublet. If the neighborhood has two H, the peak would be a triplet. Triplet means there are going to be three peaks. If the neighborhood has three H's, then the peak would be a quadruplet peak. You see so the peak would split. So for example, if I draw, और इसके अंदर splitting का ना एक और rule था, the n+1 rule. There were some exceptions. The exceptions were कि NH2 and OH peaks, they don't split or cause splitting. So what I'm going to do is I said why do they not split? Because the N has lone pairs. जैसा ये N नहीं है, it has lone pairs. तो वो lone pairs क्या करते हैं कि they cause shielding. I mean the protons over here, their magnetic field would not interfere with the protons over here because the lone pairs over here they would shield both sides. तो वो splitting वाला और interference जो होगी ना वो नहीं होगी. ठीक है? So whenever there is an N or there is an O, uh, there wouldn't be any splitting around it. ठीक है, मतलब this hydrogen proton would not be able to interfere with this hydrogen proton because of the lone pairs over here. अच्छा, anyways, let's try and sketch this. कि इसकी NMR spectrum किस तरह नजर आएगा आपको? ठीक है, I've written F1, F2. So let's focus on F3. F3 is going to be अच्छा, F3 is going to be a big peak. बहुत ज्यादा absorption होगी because there are 6 hydrogens resonating at F3, right? And it's going to be a singlet peak क्योंकि उसका जो neighboring atom है ना, it has no hydrogens, बल्कि उसके ऊपर lone pairs है. तो वो उसको बचा के रखा होगा. I mean the other hydrogen protons would not be able to interfere with them, right? So the n+1 rule would not apply क्योंकि the neighboring atom has no hydrogen in the first place. तो इसलिए this one is a singlet, single peak. फिर F2 होगी. F2 is going to be a very tiny peak क्योंकि there's only one hydrogen over there. So the absorption would be very less. So let's say this is F2, but F2 is going to be a multiplet. ठीक है, it's going to be a tiny peak, but it's going to be a multiplet. Why is it going to be a multiplet? Look at उसके neighboring पे देखो, उसके there are three hydrogens over here जो उसके बिल्कुल साथ पड़े हुए हैं. वो they would interfere with this n+1 rule. If the neighboring has three hydrogens, the peak would be a quadruplet peak. तो 4 peak में split हो जाएगा. लेकिन it also has another neighborhood on the bottom. उसके पास भी तीन hydrogens पड़े हुए हैं, वो भी इसके साथ interfere कर रहे हैं. So in total this has 6 hydrogens in the neighborhood. तो बहुत ज़्यादा पीक्स में वो स्प्लिट कर जाएगा. मतलब उसकी रेजोनेंट फ्रीक्वेंसी ना हर दफ़ा थोड़ी सी डिफरेंट होगी बिकॉज द नेबरिंग हाइड्रोजन्स द मैग्नेटिक फील्ड्स आर गोइंग टू इंटरफेयर विद दिस मैग्नेटिक फील्ड. अच्छा फिर F1 पे आ जाते हैं. F1 is going to be a large peak as well, except that F1 is going to be a doublet. अच्छा, why is it going to be a doublet? क्योंकि if you look at F1, तो these hydrogens, उनका जो neighboring carbon है, it only has one hydrogen. So if it has one hydrogen, तो n+1 rule है, तो वो दो में split होगा, तो it's going to be a doublet. और उससे वही मांगी हुई थी, उसने मांगा हुआ था कि इनमें से किन hydrogens की ना circle the protons responsible for the doublet. So this is the proton that's responsible for the doublet. This one over here. ठीक है, तो just remember कि carbon 13 NMR और H NMR में ना the only difference is the resonant frequency in both cases depends on the chemical environment, on the way they are bonded to other atoms. But apart from that, the bigger difference is कि carbon 30 H NMR के अंदर there is this concept of splitting. The hydrogen protons interfering with the neighboring atoms, which is why there's going to be splitting. ठीक है, ये सारा clear है?
Yes, sir.
Yes, sir.
अच्छा, नेक्स्ट पे चले जाते हैं कि और ये जिसने भी रिवाइज करना है मुझे बता दे कि वी कैन इन सम क्लास वी कैन रिवाइज HNMR and carbon 13 NMR in a lot more detail. अच्छा, now this one, there's a molecule of this and he's saying give the full name of the circle functional group labeled PQ and R. तो इधर ही कर लेते हैं. This is an amide. Serial bond O N के साथ, that's an amide. ये क्या चीज़ है, कौन बताएगा?
Ketone or ester?
That's a ketone. और इसका full name बताओ. What's this? The full name of this. बताएगा full name of R.
Alcohol.
Alcohol?
हाँ, लेकिन that's right. That's partially right. What's the full?
Aldehyde.
नहीं, अल्कोहल ही है. फुल नेम क्या है? फुल नेम है सेकेंडरी अल्कोहल है. 2
अच्छा.
कार्बन चेन्स के साथ अटैच्ड है. ठीक है, मतलब फुल नेम का ये मतलब होता है. फुल नेम के अंदर यू हैव टू, if it's an alcohol you have to tell it's a primary, secondary or tertiary alcohol. अच्छा खैर, you have this molecule. उसने कहा draw a circle around any chiral carbon atoms. तो ढूंढ लो chiral किधर है. बेंजीन में, रिमेंबर बेंजीन में कोई chiral नहीं होता. ठीक है, एक सेकंड मुझे उधर आने दो. अच्छा, बाकी कौन रह गया? बाकी रह गया कि CH2, तो these are not chiral. Double bond not chiral. Benzene वाले not chiral. ठीक है, so this is chiral.
Is it next to CH3 or
This one?
this? Yes.
This one? This is not chiral because it has two. I mean, all 4 groups must be
Okay.
different. So
Yes.
that's not a chiral. This one is a chiral because there's going to be one H. So this one is definitely chiral. So that's pretty much the only chiral carbon atom in the molecule. This is CH2 as well. Okay, this is C, 2 bonds, so there must be 2 H's. As the next is on warming with dilute hydrochloric acid, it splits into 2 molecules. Draw a line through the bond that's broken by heating. This is hydrolysis happening. And the bond that usually breaks is the amide link. That's going to break. And draw the structure of the smaller molecule. This side would change back into a carboxylic acid. So it's going to be, he's saying draw the molecule, it's going to be CH3. and this, and it would change back into a carboxylic acid. So remember, hydrolysis, H and OH is going to get attached back. This side would change into an amine. There would be two hydrogens. It would change into an amine, or दूसरी side would change into a carboxylic acid. Next part is suggest what would be observed when this molecule reacts with the following reagents. This is the iodoform test. याद है किसी को iodoform test किया था कि it was a test.
Yellow precipitate.
Yeah, it's going to give you a yellow precipitate, but when you have either this structure in the molecule
Methyl ketone.
or a methyl and the OH alcohol, right? So
Yes.
we need to go and have a look whether this structure is present or not. I think it's not present. It is present. This over here, a methyl with a ketone. So what's going to happen is, okay, the CH3 would break into the yellow precipitate of CHI3, which is a yellow precipitate. And because the condition is alkaline, the other side would change into a carboxylic acid. But since it's an alkaline condition, it would actually react to form a salt. So the iodoform test is positive. What about the universal indicator solution? So why would it react with the universal indicator solution? Is it acidic or not? I mean, there is no acid group. Okay, there's an alcohol group. There's an amine group. So maybe you can call it, because amines are basic, weakly basic. They're capable of attracting H plus ions. So amines are basic. So what you can suggest is that it might be weakly basic. There is no acidic group. The dissociation of alcohols, normal alcohols, is even weaker compared to water. So maybe the universal indicator solution, because it's weakly basic, it might change blue. We need to check this one. There was one basic group, so maybe slightly basic. In slightly basic, it's blue. In neutral, universal indicator is green. In strongly basic, it is purple. I said, what's the test for two? I mean, what was 2,4-DNPH used for? कोई idea? Aisha, Abu Rera?
सर क्या चीज
2,4-DNPH किधर यूज होता था? It was a test for aldehyde and ketones. ठीक है, AS में 2,4-DNPH. Aldehyde and ketones. Ketone ये पहले ही है, ठीक है? It is a ketone. I mean, this is a ketone group. So 2,4-DNPH was used as a test for identifying carbonyl compounds, aldehydes and ketones. So the test is going to be positive and it's going to give you an orange precipitate. और tolerance कहाँ पे use होता था? Tolerance होता था कि
Aldehydes.
aldehyde would change into alcohol, into carboxylic acid. Like primary alcohol would change into aldehyde, and aldehyde would get further oxidized to carboxylic acid. So to oxidize aldehydes, you would use tolerance, which would give you a silver mirror. So this is definitely not an aldehyde. I don't see an aldehyde anywhere. This का मतलब है no reaction would happen in this case. तो ये चलो ठीक है, यहाँ से we'll continue tomorrow then, ठीक है?
ओके सर अल्लाह हाफिज
Okay. और मुझे बता देना कोई अगर बीच में टॉपिक ना, if you want to study separately. चलो ठीक है. Okay, take care, अल्लाह हाफिज.